In this video, we want to take a look at vector components. This is definitely one of the more common and more powerful concepts in Physics 1, so we really want to understand this one well. All right, and so as you can see here, I already have this diagram drawn up. And now this blue line that I'm going over again in orange, this is your vector, okay? Now, so that's our vector A, right? And obviously there's a lot going on, so that's why I'm helping you to see this. So this is vector A, and we want to split that vector into components. And so often we talk about drawing the perpendicular to the x-axis or the y-axis. So there you go, there's your perpendicular line to your x-axis and your y-axis. And the reason we do that is because we don't know the length of this vector A, but we do know the tick spacing on the x-axis or the y-axis, right? That's our coordinate system. You know, we might say that this is 1 meter, 2 meters, 3 meters, 4 meters. So this would be maybe 4.5 meters, right? And so the point is, you have this coordinate system that you know the spacing of, you know those ticks, but you have this vector in it that's at some angle theta, and you don't necessarily know what the length of this vector is. And so that's the purpose. And so often we talk about drawing a perpendicular or dropping a perpendicular to the x-axis or the y-axis. And that's all we're talking about. We're just talking about getting that 90-degree angle there by going directly to the axis. All right, and so this is essentially what it would look like. And I just want you to see that when you do this, right, when you draw this perpendicular, the one that is horizontal is your x component, right? So you're horizontal there, and the one that's vertical is your y component, right? And as I've shown here, there's actually two triangles, right? There's this triangle up top, and then there's this triangle up on the bottom, and those correspond to these over here on the right. And so essentially what you need to realize is that these two triangles are completely equivalent to each other, right? So if you just took this triangle over here and you were to rotate it, right, you would just retrieve this triangle down here. And so the only difference is, well, the biggest thing to notice really is that this angle theta, right, this important angle theta actually corresponds to this angle up here, right? And that's just basic geometry. And so don't get confused and say that, oh, if this one right here is theta, then this must also be theta. No, definitely not, right? If this angle is theta, and this is a 90-degree angle total, then this top angle would be 90 minus theta, okay? And so sometimes what you'll see is the Greek letter phi or phi, depending on how you pronounce it, and that's just written like this. And that might be how they kind of show the other angle. So you'll see that sometimes. And so these are your two equivalent right triangles that you get from breaking into components. Now it's important to recognize that the sine of theta, right, is the opposite over hypotenuse, right? Opposite over hypotenuse. So what does that mean? Well, if we're looking at this triangle right here, then the sine of theta is equal to the opposite leg from theta, right? So if this is theta, then this is the opposite leg, right? Opposite the angle. And then the hypotenuse is the longest leg, right? So opposite over hypotenuse, really simple. And so opposite is AY over the vector A, magnitude, right? And so we'll just draw those bars to show that we're talking about a magnitude right now, rather than the vector itself, because the vector itself has a direction, right? And again, we're just referring to the magnitude of that vector. All right, well, what does that mean? Well, if we know the length of the vector, or excuse me, we don't know the length of the vector, but we might know the length of the individual components, right? We might know AY and AX. And so what we can do is we can say, well, hey, that length of the vector is equal to AY divided by sine of theta, right? By multiplying a magnitude to the other side and then by dividing by sine of theta, all right? And that's just something that we can do. However, I do not recommend memorizing anything like this. Never memorize these, because this will change depending on how your theta is drawn. Okay, so do not memorize this or this, just memorize this. This is what you need to know, that sine of theta is the opposite leg divided by the hypotenuse. It's just a ratio between those two lengths, right? For our particular problem, this particular triangle, we get this answer. Now, similarly, I'm actually going to erase that for now, all right? Pull these over here. Now let's also talk about cosine of theta, all right? Cosine of theta, let me use the marker here. Cosine of theta is equal to adjacent over hypotenuse. It's that ratio of those lengths. And so for our situation, cosine of theta is equal to adjacent. Adjacent just means the next side over, right? The side that is right next to it. And so that would be AX divided by the hypotenuse, magnitude of A. Okay, and that would be, again, the thing that you want to memorize up top. Memorize those for sure. You have to know these for physics. You cannot go through a physics class without knowing these. And then for your particular problem, up above, this is the answer that we get for those two ratios. Okay, and so you can see that depending on what information you have, if you have the magnitude of A and you have the angle theta, then you can solve for AY and AX. If you don't know the magnitude of A, but you have the angle and you have the length of the components, then you can solve for the magnitude. And actually, I take that back. You don't even need the angle to solve for the magnitude, because that's the next thing we want to talk about, right? That the magnitude of A is actually just the Pythagorean theorem, okay? And so all we're going to do is AX squared plus AY squared. And then if you're in 3 dimensions, you would also do plus AZ squared, okay? And so again, in 3 dimensions, you can include this Z component. If you're in 2 dimensions, you just drop it, right? AZ equals 0 in 2D. Okay, so you would just do the normal Pythagorean theorem for that one, right? And this is your normal Pythagorean theorem. And then your bigger one, bigger box here is your 3-dimensional Pythagorean theorem. And so this is, yet again, something that you need to memorize, right? You have to know this for physics. Okay, now in this problem down below, I have a little example again where I show a similar triangle, but this time I'm going to tell you. I'm going to switch to my pen here. I'm already telling you that theta is 35 degrees. Okay, now I want to know what phi is, right? And so once again, this is just a short exercise of what we showed earlier, that this whole angle from here to here is actually a right angle, right? So we should draw it like that. And that would mean it's 90 degrees, right? 90 degrees here, 90 here, 90 here, 90 here. And that's how we get 360 degrees in a circle, right? And so 90 times 4. Okay. So if that's 90 degrees, then phi is equal to, let me switch to black here, is equal to 90 degrees minus theta, right, is equal to 90 minus 35, which is equal to 55 degrees, right? And so that's your angle phi. And just important to recognize, and the reason why is because of this. So let's just start with V equals, I'm going to go off of the example from the web page here, and the link to that web page is in the description if you're watching this on YouTube. And so V is equal to 27 meters per second. Okay. And that's about 60 miles per hour. So what we're saying is that this vector here is actually a velocity vector for a car. And this car is traveling northeast, but it's not going directly northeast. That would be a 45-degree angle, right? It's actually going a little bit more east than it is going north, right? And so this is actually, I labeled it the y-axis, but this is actually north, and this one is actually east, right? But we're going to call it x and y because it doesn't really matter. And that's another important point to make, is that you set the coordinate system, All right, so v, the vector v, is 27 meters per second, and it's at this angle theta. Okay, so let's go ahead and solve for Vx and Vy, right? And this is just simple trigonometry. Okay, and so let's take a look. So we have our angle theta, and we have our hypotenuse. And this is what you really want to get good at doing very quick. All right, so what you want to determine is, okay, Vx, that's the adjacent side. And boom, right in your head, you should already be thinking cosine. Okay, and if you have the hypotenuse, remember that in the cosine formula, the hypotenuse is in the denominator, and we're trying to solve for the side. And so actually I'm going to use this up here. So if you just move the hypotenuse and do hypotenuse times cosine of the angle, you get that adjacent leg. That's what you want to do very quickly, right? That the adjacent leg, that length, is just hypotenuse cosine theta. On the other hand, the opposite leg is just hypotenuse sine theta. Okay, so down here in our example, Vx is the adjacent leg, is just hypotenuse 27 times cosine 35. And Vy is just 27 sine 35, just like that, right? And so you got to be you can be very good at doing this very quickly. Okay, and just reminding myself here, 27 sine 35, that came out to about 15.5 meters per second. Not very, there we go, 15.5 meters per second. And this one was about 22.1 meters per second. Okay. Now, let's look at the other triangle though. Okay. Now let's forget about this side, and let me move this out of the way for a second so I can erase these. Okay, let's completely forget about that triangle that we just drew. Right, and let's just do it. Let me redraw theta here. Okay. Let's use the top triangle this time. So if we're going to use the top triangle, we'll draw our perpendicular just like this, right? And this becomes Vy, and this becomes Vx up top, right? And I want you to recognize that you could just use theta over here. And if you use theta, then you'll do hypotenuse, right? So 27 times cosine of theta will give you Vx, just like we did here. And 27 times sine of theta will give you the opposite leg, Vy. And that's exactly what we had. Okay, but I don't want to use theta, right? Let's say that I want to use phi instead. Okay, well, I can do 27 times cosine of phi will give me the adjacent leg, Vy. Okay, and so Vy is equal to 27 cosine of phi, which is 55. Now Vx is equal to 27 sine of 55, right? 27 hypotenuse times sine of 55, there's your opposite leg, sine of 55, gives you Vx. And you notice that if you do this, 27 cosine 55 will give you 15.5 meters per second, and 27 sine 55 will give you 22.1 meters per second. And so you see your answers are exactly the same, right? Vy is still Vy, Vx is still Vx. Those don't change. It doesn't matter what triangle you choose. What matters is that you have the right angle, right? Depending on how you draw your triangle and depending on what angle you're using, you might get different expressions. And so one of the biggest mistakes that I see very often is that people try to associate the x component of a vector with cosine. You can't do that because down here, the x component of the vector is associated with sine, right? And so it all depends on which axis you're using, you drew your perpendicular to, right? When I drew it down here and I called this one Vy and Vx, then yeah, Vx was associated with cosine and Vy was associated with sine. But as soon as you draw a different lengths or different perpendiculars, then you get different trig functions. And so you just have to be aware of that. And so don't memorize, once again, I'm going to hit this point one more time. Do not memorize these formulas, right? Do not memorize that Vx is equal to the magnitude times cosine of the angle. That's not always true. Memorize these. If you memorize these formulas and just use those and rely on those, then you will not be wrong. Okay. Let's go to one final topic, and that is finding the angle theta when you're given the y component and the x component. And so I am just going to draw a really quick coordinate system. Got our y and our x, and let's just do some vector right at this 45-degree angle, 45 degrees, and we're just going to call this a vector A. Okay. But let's say that we don't actually know theta yet. Okay. But we know that, actually I should use a different color. Okay. Let's say we don't know theta, but we do know AY and AX. And so the formula that you want to use is now tangent. Okay. So tangent of theta is equal to opposite over adjacent. It's that ratio of the opposite side length divided by the adjacent side length. And so I want to point out really quick that this is a unitless quantity over here, and the tangent of an angle is also a unitless quantity. So let's just say that A is a vector in meters. So AY is in meters, AX is in meters. Let's just say it's some displacement vector. Then if you plug into this formula, you will get something in meters divided by something else in meters, and boom, the meters cancel, and you're just left with this ratio. And so that's what I'm talking about when I say that, you know, this is the ratio of those lengths, right? There are no meters, it's unitless. It's just a ratio, and so that's important to know, and this is the formula that you need to memorize. Or you could also memorize this one, that theta is equal to the inverse tangent of opposite over adjacent, right? We just need to undo that tangent function. How do we do that? Well, we do it with the inverse tangent. So when you take the inverse tangent of this side, it's going to cancel out the tangent, and then you are left with the inverse tangent of the right side. And so you could memorize this one as well. This one is true as well. However, there is a catch. And the catch is that this inverse tangent will give you different answers depending on what quadrant you're in. And so right now we're in quadrant 1. And so I'm just going to let you know right off the bat, in quadrant 1, no issues. Okay, there are no issues at all. But if you're in quadrant 2 and you plug in, well, you are plugging in a negative x value and a positive y value, right? Everything in quadrant 2 is negative x, positive y. And so you'll actually get an answer that puts you somewhere in quadrant 4. And so you'll end up having to add 180 degrees. And so similarly, if you're in quadrant 3, you'll get an answer. You'll have a negative y and a negative x, and that puts you, negative divided by a negative is a positive. So you actually get an answer that's some angle in quadrant 1. And so again, you got to add 180 degrees to pull you back over to quadrant 1, or from quadrant 1 back to quadrant 3. And then finally, when you're in quadrant 4, this one, it gives you a correct angle, but it's measured negative as a negative angle from the positive x-axis. And that's a little weird. So you kind of, generally we want to measure all of our angles from the positive x-axis. So an angle out here would be measured like that, maybe 300 something degrees, right? And so my point is this, right? Now that might be a lot to follow, and I don't want you to follow all of that. That is a lot of information to take in. What I want you to understand from this is that in quadrant 1, there are no issues, okay? So if you have two vector components and they're both positive, then you know that you're in quadrant 1, and you can just take that inverse tangent of the opposite over the adjacent, and you're gonna be fine, right? However, if you have, you know, -5 and 3, and then -5, -3, and 5 and negative 3. Let's say that those are the lengths of your vectors. You got your x component and your y component, right? Just 3 ordered pairs that tell you the components of your vectors. And so essentially what you need to do is this. This is really the most surefire way to get this question right. Draw a coordinate system, label it y and x, and we want to do negative 5 and 3, okay? And then you want to just draw your angle, or draw your vector, and draw your angle theta, okay? And whatever answer you get, let's say that you get an answer of 40 degrees, well, you know, now you want to analyze this graphically, right? Your calculator is not going to just tell you the right answer. You have to tell the math what to do. So this is 90 degrees over here, and so this side is 90 over here, which means this must be 50. And so then for your final answer, you can say at an angle, you know, your vector magnitude is equal to some number, and in fact, we'll just say the vector is equal to some number at 90 plus 50, 140 degrees from positive x-axis, right? Don't tell, when you write your final answer, don't tell it in terms of some random theta. Nobody knows where you drew your theta. Yes, we could look at your work, but theta is not some universally recognized thing, right? Everyone, you could draw a different theta anywhere, right? Any of these angles you could call theta. And so my point is, measure your angle from the positive x-axis and tell the person in your final answer that you measured it 140 degrees from the positive x-axis, right? Your inverse tangent, maybe it gave you 40 degrees. Okay, so what? You know, 40 degrees from where? And that's why you want to do this, right? And so, similarly, let's go down to quadrant 3, right? So let's say that we're in quadrant 3 and we get some number, and let's say that this is 50 degrees is our theta, right? Well, there's 180 degrees up here on the top half. 180 plus 50 is 230 degrees. And so when you give your final answer, say that your vector A is equal to some number at 230 degrees from the positive x-axis, right? And that's how you want to put it. That's how you should write your final answer. Now, finally, just because we're going all the way here, we'll do one more, 5 and negative 3. And let's say that that is our angle theta. Well, this is super easy because the whole circle is 360 degrees. So whatever your inverse tangent gives you, do 360 degrees minus the theta, and you'll get the answer, the angle measured from the positive x-axis, right? You always need to specify that. It's the most surefire way to make sure that you got the correct answer and that you're not just talking about some random angle theta that nobody else is really clear on. All right, this is, as I said, the most surefire way to solve this problem. And so, yes, the inverse tangent has problems when you just plug it into a calculator, but the point of physics is not to just plug things into a calculator and let the math tell you what to do. As I said before, you need to let the math, you need to tell the math what to do, right? Tell the calculator what to do. Don't let it tell you what to do. And so part of this includes just simply drawing out your vector and deciding where you're going to measure your angle from and how much do you need to add or subtract in order to make that happen.